Welcome back to Nick's Algebraics. Today I'm going to talk about hyperbolic functions. And as usual, I'll put the blank and filled out guided notes in the description so you all can follow along. So with me today, I have a random guy,
What's up? It's me.
and I have a new guest named Peanut Butter Brother.
Yo, what's up, guys? I hope you forgive me. I'm the weakest mathematically here, by a long shot. But I'm here to learn. I'm here to experience and enjoy myself, and therefore thrive and grow as a person. So, let's have a great time today, guys.
Is my introduction supposed to be that long too?
No, that's the
I'd like to go above and beyond. That's just how peanut butter brother operates. You feel me?
There you go. All right. So before you learn about hyperbolic functions, you need to be comfortable with trigonometric functions because there's a lot of similarities between the two types of functions. So let's do a quick review of trigonometric functions.
Or you could watch the video we already made about trigonometric functions.
That's true, but this is going to be from a unit circle perspective. So trigonometric functions are also known as circular functions. We know that x equals cosine of t and y equals sine of t. In this case, t is some angle. T can be anything, it's just a real number. And these functions are said to be circular because they satisfy the equation of the unit circle.
I just want to point out that the more you study trigonometry, the more you learn it has almost nothing to do with triangles and it's all just circles.
It all comes back full circle, exactly.
That was a good one. That was an amazing one.
Okay, yeah, that was kind of good.
I
Yeah,
try, I try.
we love those. We love those.
So, do you guys know what the equation of the unit circle is?
Me. I know,
Yes.
teacher.
Yes, peanut
It's
butter brother.
it's x squared plus y squared equals one, I think, possibly.
You're absolutely right.
Yes, let's go. I think that's the only one I'm gonna get right today. So I needed to get that one in.
Or just r equals 1, polar minded out there.
Also valid. So, yeah, this is related to the Pythagorean identity cosine squared of t plus sine squared of t equals 1. And like I said earlier, cosine is x, so you get x squared, and sine is y, so you get y squared, and that equals 1. So this is the graph of x squared plus y squared equals 1. You can see it's a circle with a radius of 1, and it's centered at the origin. And if you take a point on the unit circle, let me just pick a random point, let's say right here. That point has an x and y coordinate, right? The x coordinate of this point happens to be the cosine of the angle t. Let me draw t right here. So this angle right here is t.
It's a standard angle measured from like the positive x-axis.
Absolutely, yeah. And the y coordinate is the sine of that angle. It's sine of t. So yeah, that's cosine and sine. I wanted to talk a little bit about the area of the sector here that's formed by this angle t. So let me just shade that in.
Du, 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 du.
So yeah, I want to talk about the area of the sector formed by this angle t.
I know area of that sector T. And that would be A is equal to 1/2 theta r squared. But if we're using T, I guess 1/2 TR squared.
Yeah.
Yeah, I knew that one too. I just wanted to give you the glory.
Yeah, so the area A of the sector with angle T, and T is in radians, is given by A equals 1/2 r squared T. But this is the unit circle, so what does r equal?
Uno.
Yeah, you're right. So the radius of the unit circle is 1. So if I replace r with 1 here, you're just going to end up with t divided by 2. So A equals t divided by 2. All right, so that's interesting because this angle T, it represents twice the area of this sector, because if you multiply both sides by 2, you'll get T equals 2A. So T is twice the area of that sector. So let me just write that in here. So we know A equals T over 2. All right, so you just get the angle, cut it in half, you'll get the area of that sector. All right. Now that I reviewed the trig, let's talk about hyperbolas. So this should be like hopefully algebra 2 review, but if your teacher didn't cover it, then that's totally fine. You're going to learn it like on the spot now. Does anyone know the equation of a hyperbola?
I do.
Yes, what is it?
That would be x squared minus y squared equals 1 if we're doing the whole unit thing.
Yeah, you're right. X squared minus y squared equals 1. So it's literally the same thing as the equation of the unit circle, but instead of a plus, it's a minus now.
And that means the x squared and the y squared are not commutative in this equation.
That's right. Yeah. So a hyperbola is a conic section, as you can see. Like it's a cross section of a cone. And there's other cross sections. There's 4 of them. There's circles, ellipses, parabolas, and hyperbolas. They're all conic sections. So this is a cone. Like the whole thing is called a cone, and the top and the bottom parts are called half cones. If you take this cone and slice it with a plane, this is a plane right here. If you slice it with a plane that's parallel to the base of the cone, you get a circle. You can see this is the circle that results from that slice. All right, so a circle is called a cross section of a cone. If you take the cone and you slice it with a plane at some angle to the axis of this cone, then you get an ellipse. And if you slice the cone with a plane that's parallel to one of its slant sides, this is a slant side and this is a slant side. So if you cut the cone with a plane parallel to its slant side, then you get a parabola. This is the parabola right here. All right. And lastly, if you slice the cone with a plane right here, this is the plane, and it's steeper than the slant side so that it intersects both halves of the cone, you're going to get something that looks like 2 parabolas, but it turns out they're actually not parabolas. It's called a hyperbola. All right. So the x squared minus y squared equals 1 is the equation of a hyperbola. And if you graph it, it looks like this. So this is the graph of x squared minus y squared equals 1. And you can see this is one branch of the hyperbola, and this is another branch of the hyperbola. So there's 2 branches. And what's
Those asymptotes.
Yes, I was just about to mention that. What's interesting about a hyperbola is that it has asymptotes right here. These are the 2 asymptotes, y equals x and y equals negative x. And they're slant asymptotes. So that's why it's not like a parabola, because parabolas don't have asymptotes. And one other thing is that this hyperbola has 2 x-intercepts right here. How do you find x-intercepts just in general? Like if I gave you x squared minus y squared equals 1, how would you find the x-intercepts?
The x-intercepts occur at y equals 0, like on the axis. Like it doesn't move up or down. It's on that horizontal line. So you got to set y equal to 0. Solve for x.
Exactly. Yeah, so the x-intercepts are obtained by setting y equal to 0. So if y equals 0, this term is gone, and you're left with x squared equals 1. And if you take the square root, you're going to get x equals plus or minus 1. And you can see those are the x-intercepts. Negative 1 comma 0 and positive 1 comma 0. All right, so those are the x-intercepts. So you know how trigonometric functions, like I said earlier, they satisfy the equation of the unit circle?
They were very satisfactory.
Very satisfactory. But now we want functions that satisfy this equation. We want some functions that satisfy the equation of a hyperbola. So those functions are called hyperbolic functions. So anything that satisfies this equation is hyperbolic, and anything that satisfies this equation is circular. So those functions are called hyperbolic cosine and hyperbolic sine. So x equals hyperbolic cosine of t and y equals hyperbolic sine of t are hyperbolic functions because they satisfy the equation of the hyperbola x squared minus y squared equals 1. So if you take a point on the right branch of this hyperbola, let me just pick a random point. That point has an x-coordinate and a y-coordinate. And the x-coordinate of this point happens to be the hyperbolic cosine of t. And the y-coordinate happens to be the hyperbolic sine of t. And let me shade this hyperbolic sector here.
That's done.
All right. So one thing to note is that this time t does not represent the measure of an angle.
Does it represent time?
It does not represent time, sadly. What it does represent is twice the area of the shaded hyperbolic sector. So just like the trigonometric case where t represents twice the area of the shaded circular sector.
Yeah, or an angle t.
Yeah, in this case, it was an angle t. So let me write that here. So A, the area of this hyperbolic sector is just t over 2, just like last time. All right, so you can see that hyperbolic functions have the same relationship to a hyperbola that the trigonometric functions have to the unit circle. So the thing is now, like, what are these functions? Like, what the hell is hyperbolic cosine and hyperbolic sine? We need like a definition. So you know how you have 6 trig functions? We also have 6 hyperbolic functions. And of course, 2 of them are like the original ones, like the sine and cosine. So here are the definitions of the hyperbolic functions.
I don't see any t's here.
Yeah, now we have x instead of t because now we're kind of looking at it from a function like input output perspective. But yeah, so the input is x. Earlier, I just called it t. And again, it's not an angle in this case, it's just the input. So let's see. So we have hyperbolic sine. So the hyperbolic sine function, it's pronounced sinh of x. And it's defined as e to the x minus e to the negative x divided by 2. So that's interesting. Notice how this is a combination of the increasing exponential function and the decreasing exponential function. So I guess someone wanted to see what would happen if you combine this increasing exponential with this decreasing exponential and like subtract them and like average them out in a way. And they ended up calling that sinh of x. All right, the next one is the hyperbolic cosine function, which is pronounced cosh of x, like kosher. Yeah, and it's defined as e to the x plus e to the negative x divided by 2. So again, it's a combination of an increasing exponential function and a decreasing exponential function, but this time we're adding them up instead of subtracting them. Next up, we have the hyperbolic cosecant function, which is pronounced cosh, and this is the reciprocal of sinh of x. So you just flip that fraction. You'll have 2 over e to the x minus e to the negative x. And then we have the hyperbolic secant function, which is pronounced sech of x. It rhymes with like fetch. And this is the reciprocal of cosh of x. So you just flip that fraction. You prefer cosh? I think British people call it cosh. I think the
Oh, I changed my mind then.
yeah.
You're right. If the British do it a certain way, then it's wrong.
There you go. It's like aluminium.
Cringe.
But yeah, sech of x is 2 over e to the x plus e to the negative x. And then we have hyperbolic tangent. This is pronounced tanch. It rhymes with ranch. And tanch is just like the trigonometric tangent function because it's sinh over cosh, just like tangent is sine over cosine. You can see that if you do a sinh divided by cosh, the 2's are going to cancel, and you're going to get e to the x minus e to the negative x over e to the x plus e to the negative x. And finally, we have the hyperbolic cotangent function, which is pronounced koth, kind of rhymes with boat. Honestly, I've never seen this appear in a problem before, but it's the reciprocal of tanch. So if you flip the fraction, this fraction right here, you'll get e to the x plus e to the negative x divided by e to the x minus e to the negative x.
These functions all have very strange names.
Very strange names, yeah.
Still haven't told us what t is, but
Well, it's just
It represents time, dude. Come on, man. We already knew that.
it's just the input. What do you want me to say?
input.
Yeah, it's just a real number. It's just
Fine, whatever. If you say so. I do have another question about this. If there's a unit circle and you have to memorize the unit circle, is there a unit hyperbola that you have to memorize values for?
I mean, we're using the right branch of this hyperbola, but I don't think anyone's out there like memorizing cosh of like 30 or something like that. Anyway, you can see that hyperbolic functions are mimicking the trigonometric functions. Let's finally see what these functions look like. So let's do example 1. Graph and identify all key features of y equals sinh of x. So let me just write out the definition. So we have y equals sinh of x. And like I said earlier, this equals e to the x minus e to the negative x divided by 2. So again, it's a combination of the increasing exponential and the decreasing exponential. And let's just split this fraction up. I'm going to write it as 1/2 e to the x minus 1/2 e to the negative x. So I'm just dividing each term by 2. So if you want to graph sinh of x, you need to graph each of these exponential terms right here. We're gonna like look at this as a sum of two functions. Let me split this up so it looks like a sum. I'm gonna write it like this. And what I'll do is this function right here, I'll make it green.
You're like Khan Academy, but let me use a different color.
Yeah. So yeah, what I'm going to do is I'm going to graph the blue function and the green function on the same xy plane. So let's take a look at the blue function, 1/2 e to the x. So does anyone know what the y-intercept is for the graph of 1/2 e to the x?
E to the x has a horizontal asymptote, so it doesn't really intersect the x-axis.
Okay.
You want to find the y-intercepts, you say?
Yes.
That's just where x equals 0. And in this case, the answer will be 1/2. E to the 0 is 1.
Exactly. To find the y-intercept, you just plug in 0 for x, and this will be 1, and you'll just get 1/2. All right, so let me put that over here. So that's 1 point. And I'm actually not going to plug in more numbers because I know what e to the x looks like. It's a increasing exponential function. And like random guy said, the x-axis is the horizontal asymptote. So it's going to approach that. So it's going to look like this. All right. And I'm going to graph it using dashed lines because it's not the final graph. We're just going to use it to graph sinh. And now let's take a look at the green function.
Looking at it.
So we have negative 1/2 e to the negative x. So it's the same idea, but this time it's reflected twice because there's a negative in front of the x and there's a negative in front of the 1/2. That negative factor in front of the x is going to change the sign of x. So for instance, like if you have a point, x comma y, and you negate the x value, if the x value becomes its opposite, then what's that going to do?
You flip it like about the y-axis.
Exactly. It's going to reflect about the y-axis. All right. So that's what that negative does in front of the x. It's going to reflect the graph, this graph right here about the y-axis. And what is the negative in front of the 1/2 going to do?
Reflect about the y-axis.
Well, we already did that.
Oh, sorry, the x-axis, I mean. It's a lot to take in. I'm going to have to reflect on this later.
That was an amazing one. We love those.
So yeah, you're right. We're just going to graph the double reflection of the blue graph. Again, if you reflect about the y-axis, you're going to get this. And about the x-axis, it's going to look like this. All right. And the y-intercept is what for the green function?
You going to answer that?
You know what? How about this? I'll let you have this one. You know, because I'm being benevolent right now.
Oh,
I'm feeling
thank
good.
you.
I'm feeling good today. I'll let you have it. I
Thank
know
you.
the answer though. You know.
I think it's negative 1/2, but he can correct me if I'm wrong.
Well,
Good answer.
you're right. Exactly. Because
Thanks. Yep.
sorry, I'm not really good at drawing symmetries, but if you reflect it, it's going to look like that. It's going to go through negative 1/2 now because it was reflected about the y-axis and then the x-axis. And also you can just plug in 0 for x and you'll just get negative 1/2. That's probably the easiest way of doing it. So it's going to look like this. We got this point right here, and it's going to look like this. And again, I'm going to make it dashed because it's not what we're trying to graph. It's not like our final answer. All right, so let me just label this. This is y equals 1/2 e to the x. And this right here is y equals negative 1/2 e to the negative x. Okay, cool. So what this sum says right here is that the blue output and the green output are going to add. So for instance, at 0, at x equals 0, the blue output is half and the green output is negative half, and those are going to add and give you 0. The graph of sinh of x is going to go through 0, comma 0. So that's the first point of sinh of x. So now let's draw the rest of sinh. Notice that the green graph is going to 0. It's actually going to 0 really, really fast because it's exponential. So as x gets big, as x goes towards infinity, we know that negative 1/2 e to the negative x is going to go to 0. Let me write that out.
Oh,
So
goody. I thought there wouldn't even be limits in this video.
so the limit of negative 1/2 e to the negative x as x approaches infinity is 0. As this goes to 0, what's going to happen is the blue graph is going to dominate. It's going to take over. So you're basically adding the blue y values to the green y values that are almost 0. So sinh of x is going to end up looking like the blue graph as x gets big. All right. But the graph of sinh is never going to become the blue graph. It's going to get close to it. All right. So let me write that out. So since the limit of this function as x approaches infinity is 0, then that means sinh of x is going to approach this function right here, the blue function, 1/2 e to the x. And again, this is as x approaches infinity. All right, so sinh is going to look like this. That's like the right half of it. And you can make the same argument going towards negative infinity. As x goes to negative infinity, the blue graph is going to die out and the green graph is going to take over. And the green graph is like negative, so the negative values take over. So the positive values are going to go away. The green graph is basically going to attract the graph of sinh to itself. All right, so let me write that out. So the limit of 1/2 e to the x as x approaches negative infinity is 0. So sinh of x is going to approach the green function, which is negative 1/2 e to the negative x as x approaches negative infinity.
It's taking a lot of time just to graph sinh. Video is going to be sinh. You can just go on Desmos. It takes you a second.
Wait till you get to cosh.
I'm going to have to speed that one up a little.
Yeah, I'm going to try. So yeah, the graph of sinh is going to get close to the green graph. So the green graph is going to take over and it's going to look like this. All right, so
This looks vaguely cubic.
yeah, it looks kind of cubic.
X to the third power. It's the closest thing I've seen to a triangle this entire video.
Yeah. But yeah, this is y equals sinh of x. All right, isn't that fantastic?
Amazing.
And again, it's never going to touch the green graph. It's just going to approach it. So basically 1/2 e to the x and negative 1/2 e to the negative x, those are the asymptotes of the graph of sinh of x. They're not like the typical horizontal asymptotes, but they're still asymptotes.
These are really funky asymptotes.
Yeah, very funky. So now let's talk about the features, these key features. So what does it look like the domain of sinh of x is?
I'll take this one since it seems to be a lot harder of a question. I don't want to stump you here. I think it might be negative infinity to positive infinity. I would assume.
That's absolutely right. Yeah, the domain is all reals, which is basically what you said, negative infinity to infinity. And what about the range?
I think it would also be all real numbers.
Exactly. Sinh could be anything, basically. You can input anything, you can output anything. All right. And is sinh an even function, an odd function, or neither?
Even.
Well,
I would like to usurp this question.
You may.
I will disagree. I think it's odd, but he's trying to test me. He's trying to see if I pick up on it.
You caught that. That was good. That was good. I just had to test you to make sure you weren't going to be swayed by, my answer just because, I happen to be correct.
of course. Okay. So this is an odd function. Remember, odd function means that the graph has symmetry about the origin. If I rotate this graph about the origin like 180 degrees, it's going to map onto itself. right? So that's what it means for a function to be odd. And algebraically, it means that sinh of negative x equals negative sinh of x.
Well, why parentheses on the negative one, but not on the other one?
Well, because of the negative, pretty much.
This gives an itch in my brain. I hate looking at that. Please put parentheses around the other one.
Okay, sure.
It's much better.
I just scratched your brain.
Yeah.
So, where is it differentiable? On what interval is it differentiable?
If I may, I believe it is differentiable on the open interval from open from negative infinity to positive infinity. It can't be differentiable at those values because
At infinity. But
yeah. What is sinh of infinity? What is d dx sinh x of infinity? Who can say?
yeah, who knows? But yeah, you're right. It's differentiable on all real numbers, on all reals. It's
I
different.
went into too much detail.
Yeah, you kind of and it's differentiable for all x because e to the x and e to the negative x are both differentiable. Actually, I should talk about what differentiable means for those who don't know. So,
If you watch a hyperbolic trig video, they probably have some idea.
yeah, hopefully they know. But if you don't know that word, it basically means that the derivative exists. So it means that the graph is smooth. There's no sharp corners, and you can basically draw a tangent line at any point.
And it's continuous.
Yeah. So actually, I'm glad you brought that up. Notice how I don't have like a continuous category. I'm not mentioning continuity because when you say that a function is differentiable, then by default, it's also continuous. So it would be redundant for me to say that the function is differentiable and then say it's continuous.
The converse is not necessarily true though.
That's true, exactly. If it's continuous, that doesn't mean it's differentiable. But if it's differentiable, it's automatically continuous because differentiability implies continuity.
Since we're reviewing even odd functions differentiability, why don't we just cover all of calculus in this
Yeah,
video? Why don't we just do all of math? You can call this video like a speed run. You should put that in the title.
literally limits, differentiability, continuity, exponentials, all of it.
Literally everything except triangles.
Conic sections, all of it. Yeah,
Everything but triangles has been in this video.
yeah. So one last thing, where is it increasing?
If I may,
Yes.
graphically, if you were to draw a tangent line at any point, that the slope of the tangent line would always be positive. That implies the derivative is positive everywhere. Therefore, it is an increasing function.
Exactly. It's increasing everywhere. So increasing on all realms. And that's cool because when a function's increasing all the time, then that makes it a one-to-one function. I don't know about you, but like these features are really nice. Domain all reals, range all reals, differentiable everywhere, increasing everywhere. That's like pretty nice. That's a pretty good function there.
It's pretty solid.
Yeah, so any questions on sinh before I move on to cosh?
I'm so sick of cinch. I'm so
Cosh is slightly easier to graph, I think. So yeah, let's graph cosh. Let me write the definition of cosh first. So y equals cosh of x. That equals e to the x plus e to the negative x divided by 2. All right, so again, it's a combination of an increasing exponential and a decreasing exponential function. So let me just write it like I did last time. I'm going to split this up into 1/2 e to the x and 1/2 e to the negative x. And just like last time, I'm going to graph the blue and the green function on the same grid. So let's take a look at 1/2 e to the x. Well, we already graphed that right here. So again, the y-intercept is 1/2 because when you plug in 0 for x, you get 1/2. And it's increasing, so it's going to look like this. Yeah,
And the other one's just going to be reflected about the y-axis, same thing.
exactly. Yeah. Yeah, and this one right here, like I said earlier, you put a negative factor in front of the x, that's going to reflect the blue graph across the y-axis. So it's going to look like this. And it's going to have the same y-intercept. So we're going to use these two to graph the sum, basically, to graph cosh. So the blue output and the green output are going to add. So for instance, at 0, the blue output is half. The green output is also half. So those are going to add to give you 1. So that's our first point for cosh. the graph of cosh is going to go through 0, 1. That's the y-intercept. All right, so now we need to graph the rest of it. So notice that the green graph is going to 0 very quickly, again, because it's an exponential function. So as x gets big, as x goes towards infinity, we know that 1/2 e to the negative x goes to 0. So if this goes to 0, then the blue graph is going to dominate. It's going to take over, right? Here, let me label these. So this is 1/2 e to the x, and this is y equals 1/2 e to the negative x. And like I said earlier, the limit of 1/2 e to the negative x as x approaches infinity is 0. So this term is going to die out, and what's going to happen is the blue graph is going to dominate. So cosh of x is going to approach 1/2 e to the x as x approaches infinity. All right, so it's going to look like this, something like that. And just like last time, it's not going to become the blue graph. It's just going to get very close to it. And you can make the same argument just like last time going towards negative infinity. So as x goes to negative infinity, the blue graph is going to go to 0. And cosh of x is going to get close to the green graph because the green graph is going to take over. All right. So let me just write that out. So the limit of 1/2 e to the x as x approaches negative infinity equals 0. So cosh is going to approach this green graph, which is 1/2 e to the negative x as x approaches negative infinity.
You could have like copy and pasted some of those limits from the previous problem.
Yeah, I should have done that.
It's okay. It's a speed run, so take as much time as you want.
Yeah.
What I'm noticing is that the sinh graph is impersonating a cubic function, and this is impersonating a quadratic function.
I was just about to say the same thing. I mean, that is so true. Yep, it's a good observation.
This is Among Us, but with math functions.
There you go.
No way you just said that. Oh my God. My brain hurts. The memories of Among Us are coming back. They're flooding back into my head. Now I want to play Among Us.
But yeah, that's the graph of cosh of x. And yeah, you're right. Some people say that it looks like a parabola, but
But it has asymptotes.
there you go. Exactly.
Yep.
It's not a parabola because it has asymptotes. Another thing is that right here, it's increasing very quickly, right? It has that exponential growth to it. So it's not a parabola because a parabola is a second degree polynomial. Like for example, if you have y equals x squared, that's a power function, but
Right. Exponentials grow faster than polynomials.
exactly. Whereas this thing is an exponential function and it's increasing exponentially as you go to the right. So it's much more powerful than just like y equals x squared, just like some kind of quadratic function. But that's the graph of cosh. So now let's look at the properties of this function. So what does the domain look like? Oh, by the way, let me label this. This is y equals cosh of x.
Thanks. I wasn't sure what function this was until you wrote that.
Yeah.
Same, me neither.
So what's the domain?
It is all real numbers.
There you go.
There you go. Yeah, the domain is all reals. What is the range?
It appears to include 1 and go to infinity. So you put a little bracket by the 1.
Exactly. There you go.
Yep. Random guy. Good job.
That basically means that the absolute minimum point is 0, 1. So the function is decreasing from negative infinity to 0, and then it's increasing from 0 to infinity. But what about symmetry? Is this an even function, odd function, or neither?
You want to answer that?
Sure. It is in fact an even function.
There you go. Yeah. It's even because it has symmetry about the y-axis. That's what it means for a function to be even. And algebraically, that means that cosh of negative x equals cosh of x.
I just realized it doesn't say increasing under differentiable.
Yeah, I kind of removed it for that one because I purposely put it for this one because it's increasing always, and I just want to make the point that it's 1-to-1. But yeah, for this one, it's okay. We'll just leave it out. And so where is it differentiable?
I would say that this is differentiable over all the real numbers. I might even say.
Exactly. Differentiable
I
for,
would say the same.
that's right, for all x, because this is made up of e to the x and e to the negative x, and they're both differentiable. And again, by default, it's continuous. All right, so you can see that the graphs of y equals cosh of x and y equals sinh of x are very different. And they're also very different from sine and cosine because they're not waves.
And x cubed and x squared.
Yeah, and of course they're different from x cubed and x squared.
These just don't belong anywhere, do they?
They're very special. Yeah.
They take the short bus to school.
Yeah. But let's just briefly talk about the applications just for a quick.
Applications?
Yes.
So, cosh, this function is highly useful when you're looking at the curve that a cable forms when it's hanging from two poles.
A catenary or whatever it's called, right?
Yeah, a catenary curve, exactly. You've probably seen this before. You've seen those power lines outside that hang from pole to pole.
Yep.
So,
No, I've never seen that. I live in an undeveloped part of the world.
oh, how dare I
Yeah.
assume?
It's true of an internet connection, so I can be on this call.
Yeah. So this cable, it's not going to be connected like this. It's not going to be just a straight line. It like that, like
I
stiff.
mean, if it's taught,
Yeah, unless it's super taut. But the thing is, it's going to be under the influence of gravity. It's going to have tension. A bunch of physics stuff is going to happen, and it's going to get pulled down a bit. And it's going to form this curve. And this thing can be modeled using cosh. It's proven using physics. You can use the laws of physics and just take into account gravity and tension and whatever, and you can prove that the shape of this cable involves cosh.
very important information when they were designing telephone poles. I think they definitely took this into account. They definitely didn't just cut a piece of wire and just hang it between two poles. They needed to know cosh.
Absolutely. And as Random Guy said, this is called a catenary curve. It's the shape that's formed by a flexible like chain or rope when it's suspended by its ends and it's allowed to hang freely under the influence of gravity.
Exactly. And fun fact, the guy who created the first telephone poles, like created the first idea, was actually arrested for beating up homeless people. I don't remember when exactly it was, but he was actually beating up homeless people. He had like bodies, was like smashing them over people's heads and stuff like that. So he was arrested and charged for the crime. Just fun fact.
Oh wow. I did not know that. That's crazy.
Yeah. I'm still not sure that I know it. Cinch is useless because I've never seen a cinch shaped telephone line.
I think that's because he was arrested, so he didn't have a chance to present his theory.
Maybe if gravity points in two different directions, you can do this.
Yeah, maybe.
Possibly, or if he gets released on parole.
Yeah. But yeah, so remember how I was telling you at the start that hyperbolic functions mimic trigonometric functions, even though the graphs are very different because, like I said, there's no waves. The identities are almost identical to like the trigonometric identities. So the double angle identity for sine and cosine?
Sine of 2x equals 2 sine x times cosine of x.
So yeah, that's sine of 2x, and it's the same thing with hyperbolic sine and cosine, because sinh of 2x equals 2 times sinh of x times cosh of x. All right? So it's literally like the same thing. Okay? It's kind of weird. So all the identities that you guys have learned for trigonometric functions, they're mimicked by the hyperbolic functions. Either exactly the same or like differs by like a plus or a minus. And the same goes with the derivatives. So you know how the derivative of sine is cosine? It turns out that the derivative of sinh is cosh. Let me show you why. So these derivatives are actually very easy to calculate because it just involves derivatives of e to the x. So we need to find dy dx for example 3. We have y equals sinh of x. So what is sinh, guys?
E to the x minus e to the negative x all over 2.
Yeah.
There you go. So we just need to take the derivative of this. We want dy dx. One thing we're not going to do is we're not going to use the quotient rule. Even though we're dividing doesn't mean we should use the quotient rule because we're dividing by a constant.
Constant multiple. Although you could do the quotient rule if you want to torture yourself.
That's true. That's very true. But yeah, the 2 is the constant. If you're trying to take the derivative of a function over a constant, you just take the derivative of the numerator and just leave the denominator alone. So we have to take the derivative term by term. So what's the derivative of e to the x?
Isn't it just e to the x?
It's itself, yeah.
This is the hardest derivative I've ever had to learn.
And then minus, what's the derivative of e to the negative x?
Chain rule it.
Yes, we have to use chain rule.
Yeah.
So you get itself times the derivative of negative x, which is just -1. All right. And then again, just leave the 2 alone. It's just a constant. So divide by 2.
Geez, that looks just like cosh of x.
Exactly. We have a double negative, so we can make that plus. And you end up with dy dx equals e to the x plus e to the negative x divided by 2, which is exactly cosh of x. All right. So the derivative of sinh is cosh. So isn't that crazy?
It's so crazy. Absolutely insane.
Okay, let's do part B now. You know what? Let's look at the graph actually.
Let's
Why
do
are you
it.
gonna do this to me?
Yeah, so the derivative of sinh is cosh. So that means the slope of the tangent line at any point to the sinh graph is going to be the same as the y value of the cosh graph. I mean, I'm not going to like waste our time and look at the slope of the tangent lines everywhere, but we're going to look at the trend. So first of all, let's look at the slope of the tangent line at this point 0, 0. The slope of the tangent line at 0, 0, it looks like 1. I'm just kind of estimating here. Let me use a more visible color like this. So it looks like M, the slope of the tangent line, is just 1 there. And if you look at the graph of cosh, it goes through the point 0, 1. All right, so cosh has a y value of 1 at 0 because the derivative of sinh at 0 is 1.
You lied. You weren't guessing.
Yeah, I fooled you. So notice also that the graph of cosh is always above the x-axis. It's always
Oh yeah, because the slope of the tangent line of sinh is always positive. It's always an increasing function.
Exactly, because sinh is always increasing. If f prime of x is greater than 0 on some interval, then f, the original function, is going to be increasing on that interval. All right. Anyway, so that's the geometric interpretation of it. So now let's look at the derivative of cosh of x. So it's the same idea. We know cosh, we're going to use like the exponential definition. So cosh is e to the x plus e to the negative x divided by 2. All right.
Well, you do some derivative stuff. 1/2 in the front, then you got that e to the x, and then you got to do like the minus e to the negative x from the chain rule. And yeah, sinh.
Exactly, yeah. The derivative of e to x is just e to x. And then for this one, you have to use chain rule and you get that negative, and the 2 just stays the same. And yeah, this right here is just sinh of x.
Which is weird that it's not negative because the derivative of cosine is negative sine.
Yeah,
True.
Has anyone ever called these cosine and shine?
not that I know of. But yeah, that's actually the minor difference between the trigonometric and the hyperbolic derivatives is the derivative of the trigonometric cosine is negative sine, but it turns out for the derivative of cosh, it just sinh. So there's no negative. That's just great. It's just sinh of x. So let's just look at the geometric interpretation
Yay.
briefly.
Briefly,
Very briefly, let's just look
we
at
get the idea.
briefly, let's just go back to the graphs and compare the slopes of the tangent line. So if you calculate the slope of the tangent line of cosh at 0, 1, here, the slope of the tangent line, M, is 0 because it's just a horizontal line. And notice that the y value of sinh at 0, it's 0. And one other thing is notice how sinh is negative. It's below the x-axis from -infinity to 0. And that means cosh is decreasing. And also the graph of sinh is above the x-axis from 0 to infinity. It's positive, and you can see that cosh is increasing. So yeah, and here's a table of the other derivatives. I'm not going to go through all of it, but it's very easy to find the derivatives.
Are you sure? You sure you don't want to do the derivative of all of them and then graph them all?
Maybe next time, but I'll just briefly talk about it. So if you want to find the derivative of hyperbolic tangent, you can use this exponential definition right here, but it's going to be easier to write it as sinh over cosh and then just use the quotient rule. All right. And same thing with hyperbolic secants. Like you can just write it as 1 over cosh and use the quotient rule or the chain rule.
By the way, the sinh and cosh both satisfy the differential equation y equals y double prime.
That's right. Exactly. Because you take
Since we're doing all the calculus in this video, we might as well do differential equations.
absolutely, yeah.
Definitely.
Anything but a triangle.
Yeah, anything but a triangle.
The negative signs in here are a bit different than what you would expect from the regular trig functions.
I agree.
Yeah, that's right.
Reciprocals all have that negative.
Yep. I taught him that.
Yeah.
He did teach me that.
Yeah, these hyperbolic functions, they mimic trigonometric functions, but yeah, they don't always mimic their sign. That's the thing. But let's do example 4. So this
Easy. This is so easy. By definition of the x squared minus y squared equals 1. Boom. 3D. That's the way you define the functions to begin with.
Okay.
We're done. That's the end of the video, guys.
See you guys in the next videos. But yeah, this comes from x squared minus y squared equals 1, the equation of the hyperbola. But yeah, let's prove it using the exponential definitions of quotient.
This is going to be so much algebra.
Yeah, I'll try to skip some steps. So anyway, we'll start off with the left side of the equation. So we have cosh squared x minus sinh squared x. So cosh is e to the x plus e to the negative x divided by 2, and we're squaring it. And sinh is e to the x minus e to the negative x divided by 2, and we're squaring that also. All right. So when you're squaring a fraction, you need to square the numerator and the denominator. So if you square the denominator for both of them, you're going to get 4. And we're going to subtract them, so we can just create one big fraction with a
I think that factoring and foiling video is going to come in clutch right now.
It's going to come in very clutch right now. So
I wasn't in that video.
But yeah, so this is just e to the x. We're squaring it. So it's e to the x plus e to the negative x times e to the x plus e to the negative x. And then we have minus. Same thing right here, but with a minus. Okay, so we just need to use the FOIL method. Let me just do a little copy pasting. So first, e to the x times e to the x is e to the 2x. Yeah, and then we have outer e to the x times e to the negative x, and inner is the same thing, e to the x, e to the negative x. So when you combine it, you're going to get 2 e to the x, e to the...
I wasn't in the foil video, so I didn't get to say this, but I never memorized foil. I know how to do it, but I never memorized the acronym.
How foolish.
I never needed it.
He's just built different. It's okay. And then we have e to the negative x times e to the negative x. That's e to the negative 2x.
Yes.
And then minus, be careful here. We're subtracting this whole thing. So I'm going to put one big parentheses. So same thing, e to x times e to x is e to the 2x. E to the x times negative e to the negative x. And then same thing right here, e to the x times negative e to the negative x. That's going to be negative 2 e to the x, e to the negative x. And lastly, we have negative e to the negative x times negative e to the negative x. That's positive e to the negative 2x.
Well, e to the x times e to the negative x is just 1.
That's right. Before we get to that, let's do some canceling. This is the best part. You can see e to the 2x, e to the 2x, we're subtracting. That's going to cancel. E to the negative 2x minus e to the negative 2x, that's going to cancel. And we have 2 e to the x times e to the negative x minus negative 2 e to the x, e to the negative x. So that's going to combine into 4 e to the x, e to the negative x, all divided by 4.
Nice.
Yeah, so that looks way cleaner. And then the 4s are going to cancel. And let me just do this on the side here. E to the x times e to the negative x. Since the bases are the same, you can just add the exponents. So you'll get e to the x minus x, which is e to the 0, which is 1, just like random guy said. You can also think of e to the negative x as 1 over e to the positive x. And what's going to happen is these will cancel and you'll get 1. So that's another way of thinking about it. But yeah, this is going to equal 1.
You proved the identity.
Yes. We proved this hyperbolic identity.
Yes.
Lots of canceling, but yeah, you just end up with 1. So,
Yeesh.
So this hyperbolic identity is analogous to the Pythagorean identity sine squared plus cosine squared equals 1. But the Pythagorean identity has a plus instead of a minus.
That's a unit circle, not a unit hyperbola.
Exactly, yeah. And we have variations of this identity right here. And you know how when you take the Pythagorean identity and you divide it by cosine squared or you divide it by sine squared, you get the two variations. So we're going to do the same thing here for this hyperbolic identity.
We're not going to derive it on the spot, are we?
We sure are. Let's do it.
It's such a long video.
It's fast. So let me just write this out. These are the variations. So what I can do is I can divide both sides of the equation by cosh squared. Cosh squared divided by cosh squared. And then we have minus sinh squared over cosh squared. And this equals 1 over cosh. Oh, wait, I didn't square that. Cosh
I
squared.
was a bit pointing right on that.
Yeah. And then 1 over cosh squared. Okay, I'm glad I caught that fast. So cosh squared over cosh squared, that's just 1. Sinh squared over cosh squared is just tanh squared. Sorry, it just sounds so funny, but
Not just me, right? These names are a little bit.
yeah.
A little funky.
Then 1 over cosh squared is sech squared.
Fetch.
Oh my gosh. This sounds like I'm speaking another language.
Yes, it
It
does.
sounds like a different word.
Yeah. And then let's look at the other variation, one last one. It's the same idea. You start off with cosh squared minus sinh squared equals 1, but instead of dividing everything by cosh, now I'm going to divide everything by sinh squared. The beauty of copy and paste. Cosh squared over sinh squared is hyperbolic cotangent. Yeah, it's coth squared.
Sorry.
Or coth is, I think, the British way, but
No, the British are wrong. They lost the Revolutionary War, so they're wrong.
and then sinh squared divided by sinh squared is just 1. And then 1 over sinh squared is cosech squared. Oh, wait, whoops. Cosech.
Coach.
All right, so those are the 3 hyperbolic identities. The cool thing is that you don't need to memorize all of these. You just need to memorize this one. From that, you can derive the rest. So
That's what I did with the regular trig identities on exams when I couldn't remember them.
Yeah,
To forget, like, is it 1 minus the thing or is it the thing minus 1? It's like
exactly.
complicated.
From that, I was just like, hey, random guy, let's simplify this, let's make this easier for you. And I was like, here, boom, boom, boom. And he did it very well. He's a good student.
Thank you. You were a great teacher.
You're welcome. I taught him the skibbity ways. Very nice.
Wonderful. But yeah, if you were to ask me like 3 minutes ago, can you tell me what the variations of cosh squared minus sinh squared equals 1 is? I literally would not be able to tell you. Like I would have to do this all over again.
Skill issue.
Yeah. My damage is brain.
Not enough skibbity tokens.
Yeah, I just can't remember stuff in general. So anyway, let's do example 5 now. Example 5 says if tanh of x equals 12 over 13, find the values of the other hyperbolic functions at x.
I have ideas for this.
Yes, what do you think?
Well, originally, when I looked at this, my brain went to regular trigonometry. It was, I gotta draw a triangle. I gotta do some Pythagorean things. But since we're not allowed to use triangles in this video, apparently,
That's
I
right.
can just say that tanh is sinh over cosh, and that's like 12 over 13, right? So that implies sinh is 12, cosh is 13. And then you just do the reciprocals for the remaining 3, and boom, you're done.
Sinh is 12 and cosh is 13? Not really.
What do you mean, not really?
Because, well, okay, first of all, I want to say that you're right. You should not be drawing a triangle here because this is hyperbolic trig. It's not regular trig. So if
We
you
draw hyperbola instead?
you said that tanh is sinh over cosh, and tanh is 12 over 13. So you might think sinh is 12 and cosh is 13. But that's not necessarily true because what if sinh is
Oh yeah, I get it. Yeah, I
like
guess different.
sinh
Yeah.
can be like 12 over 7 and cosh can be like 13 over 7 and you can
I guess. I guess.
But before we even get to sinh and cosh, like let's just start with the obvious. If we have tanh, we can easily find coth, the hyperbolic cotangent, because it's just the reciprocal, right? So coth is just 13 over 12. So just start off with that.
We're gonna use the Pythagorean thingies and like do some solving.
That's right. Let's see. We have tanh. What we can do is using that, we can find sech. So using this hyperbolic identity. So we know that 1 minus tanh squared x equals sech squared x. So let's just solve for sech. You just have to take the square root. So sech of x equals the square root of 1 minus tanh squared. Tanh is 12 over 13, so that's 12 over 13 squared. And again, we're taking the square root of all this. It was sech squared and now just sech.
Plus or minus or no?
That's a good point. Do we put plus or minus? Because we're taking the square root of both sides. And we actually just do plus because if you look at the graphs, we know that cosh is always positive. It's always above the x-axis. So sech, which is the reciprocal of cosh, is also going to be always positive. So you don't put plus or minus. It's just going to be plus. All right.
Well, I never got questions like this in Calc 2.
Now let's just clean this up a little bit. So 12 over 13 quantity squared, you have to square the 12 and the 13. So it's 144 over 169. And I'm just going to write the 1 as 169 over 169 because I want the denominators to be the same. And we're taking the square root of all this. So 169 minus 144, that's 25. So you're left with the square root of 25 over 169.
The square root of all that, and that's gonna be 5 over 13.
Exactly. Square root of 25 is 5. Square root of 169 is 13. So that's sech.
These numbers remind me of like what do you call those things? Pythagorean triples or whatever.
Yeah.
I was thinking the same thing.
And then sech, from there, you can easily find cosh because cosh is just the reciprocal, right? So if sech is 5 over 13, cosh is just going to be 13 over 5. All right. And what's left? We need sinh and cosech. How are we going to find sinh?
Why don't you scroll to them identities up there?
Let's see. We could use this identity, but there's actually an easier way. We know that tanh is sinh over cosh. So I think that's a better way because you don't have to do square root and all that stuff. So tanh is sinh over cosh, and we want sinh. So I need to multiply both sides by cosh, and you'll get sinh is tanh times cosh. So tanh, that was given to us. That's 12 over 13. Cosh, we just found, is 13 over 5. So the 13s are going to cancel out nicely, and you'll get just 12 over 5.
And cosech is then 5 over 12.
Exactly, just the reciprocal. All right, so that's how you find the 5 other hyperbolic functions at x. You just use those identities. No triangles needed. All right, let's do some more algebra.
Oh, this one looks easy enough.
Yeah, so I'm not doing too much calculus. I'm doing a lot of algebra here and a lot of graphing because the calculus of hyperbolic functions is just the calculus of e to the x pretty much. So that's why I'm doing a lot of algebra. But what we have here is we have hyperbolic tangent composed with twice ln x. This thing is gonna drastically reduce and simplify because you're composing natural log with a function that involves e to the x. Because again, hyperbolic functions are defined using combinations of e to the x, e to the negative x, or quotients of combinations of e to the x or e to the negative x. And we know that e to the x and ln x are inverse functions. So if you compose them, if you have e to the ln u just in general, that's going to equal u. They're going to undo each other. All right. So you get a cancellation. And again, that's because e to the x and ln x are inverse functions. This is the inverse function property. So we're trying to find tanh of 2 ln x. So remember the definition of tanh, it's e to the x, but now we're plugging in 2 ln x minus e to the negative x, but now it's e to the negative 2 ln x over e to the x, which is now e to the 2 ln x plus e to the negative x, which is now e to the negative 2 ln x. So the issue is, let me put this in green.
The issue is that you can't solve this unless you watch that logarithm video we made.
Yes, there you go. Please watch my log video and you'll know exactly how to cancel things out here. But we want e to the ln. This is 2 ln u right now. You can't cancel the e and the ln and say this is 2u. Like that's not how it works. We want the e to like touch the ln basically. So to do that, we have to use our log properties. So can anyone tell me what I can do with these 2's and negative 2's? So we have e to the ln u.
Would my co-guest like to answer this one?
I could, but I want to challenge you today. I need to make sure you grow from this. So let's hear your answer.
Okay, okay. We'll use that power property that logarithms have. We'll put that 2 as an exponent. E to the ln of x squared for that one term. And then we're going to add to that, or subtract, I mean, e to the ln of x to the negative 2. And then we're going to divide by all that thing, but now it's a plus. And then happy times occur.
Exactly.
Good things happen. That e and that ln, that cancels.
Yep, because of that inverse function property right here. We have e to the ln u, the e and the ln's all cancel. Yeah, so the trick is you need to move the coefficient of ln to the exponent of its argument. And yeah, if the e's and ln's cancel and you're just left with x squared minus x to the negative 2 over x squared plus x to the negative 2.
Is that simplified enough for you?
No. So
We haven't done enough algebra in this video.
we need more algebra. This is a complex fraction.
Multiply by x squared over x squared.
Yeah, just to clean this up a little bit, let's multiply the numerator and denominator by x squared. So we need to distribute. So x squared times x squared is x to the power of 4. X to the power negative 2 times x squared, the exponents add, you get x to the 0, which is 1. And then same thing in the denominator, but now there's a plus in the middle.
An issue with this. We have a domain restriction problem because we used a natural logarithm. So it's like x strictly greater than 0, right?
Yeah, that's right. I mean, I don't really care about that right now, but
Minus 1,000 over.
yeah.
X greater than 0 on every single step.
But this result's very interesting because when you compose a hyperbolic tangent with natural log, you end up with a rational function. A rational function is just a polynomial divided by a polynomial. I don't know. I find that really crazy. Okay. To finish off today, I want to do 2 integrals.
Yes.
So
Oh, goody. I love integrals.
for the audience watching, I know some people learn hyperbolic functions after the integral chapter, and sometimes they learn it before the integral chapter. So if you haven't learned about integrals yet, you can just like skip to the end. I put this to the end for a reason. But if you do know about integrals, then stick around.
To skip, you'll reduce the average watch time on the videos.
It's okay. Only like 2% of people are going to reach this point. So if you're here, you're probably like a
Leave a
really,
comment saying we should give you a special phrase to say if you made it this far.
yeah, say,
I have an attention span greater than a goldfish.
yeah, something like that. Exactly.
Yeah, say that specific phrase and we'll know you made it this far.
Yeah, perfect. Let's do these 2 integrals. What do you think we should do for the first integral? We have the integral of cosh over cosh squared minus 1.
An idea comes to mind.
Let's hear
You
it.
can use a hyperbolic type of identity. You nodded when I said hyperbolic. Like, that's so vague. How'd you know what I was going to say?
The moment you said hyperbolic, I was like, he knows. Like,
You simplify the denominator using Pythagorean looking things.
yeah, okay, there you go. It's Pythagorean looking, which is hyperbolic. So, yeah, we're going to use cosh squared. We have to just rearrange some stuff. So,
Subtract 1, add sinh squared, and you get that nice substitution.
yes. So add sinh to both sides, you'll get cosh squared equals 1 plus sinh squared of x. And if you subtract the 1, you'll get cosh squared minus 1 equals sinh squared. All right, so this cosh squared minus 1, I'm going to replace it with sinh squared. So this equals the integral of cosh over sinh squared dx. Okay, that looks a little cleaner. Now what are we going to do?
So we have cosh over sinh squared. which can be rewritten as cosh over sinh times 1 over sinh, which would be cosh times cosh. Oh, that's so weird to say.
Yes. Yeah, we can split this up into cosh over sinh times 1 over sinh. You can also do a U substitution too.
We were trying to practice our hyperbolic trig identities.
Yeah, so I agree with this way for now because let's practice. So we can split that up and we know cosh over sinh is coth of x and 1 over sinh is cosh.
Well, this looks like a simple thing to do if we just look at our identities from earlier, the derivative. So yeah, it looks like it should be negative cosh.
Yeah, exactly. Yeah, of course, plus see, it's cosh times coth without the negative, so it's the derivative of negative cosh.
The answer is C minus cosh of x.
That's a valid way of writing it. That's a very
Sometimes I like to write minus C because it's a constant. Who's to say it isn't negative, right?
That's true. That is absolutely right. But yeah, so it's just that derivative thing like in reverse. So negative cosh x plus c.
No, you should write negative C minus cosh. It's not wrong.
What do you do, Dennis?
Do what?
Nothing. Continue.
Okay. Last integral for today. For this one,
I have an idea.
yes, what do you think?
My brain says do integration by parts, but my heart says do something other than that. Writing. Well, copyrighted music, get this video striked. I was gonna say
YouTube was a parody.
write the exponential definition of cosh, and then it should simplify.
Exactly, yeah.
Thinking the same thing. I was about to say that.
So we're going to use the exponential definition of cosh to evaluate this integral. But we're doing cosh of 2x. So we're going to replace all the x's with 2x. So cosh is e to the x, now it's e to the 2x, plus e to the negative x, which is now e to the negative 2x, over 2 and dx. And you can see that the 2's nicely cancel here. And what am I going to do with these e to the x's?
Distribute.
Distribute.
Let's,
Yeah.
yeah, let's distribute. So this is
We need distributors.
yeah. So when you distribute, you get e to the 3x times e to the 2x. You add the exponents, you get e to the 5x. And then e to the 3x times e to the negative 2x. Again, you add, you get e to the 1x, which is just e to the x. So what's the integral of e to the 5x?
We shall use integration to solve this problem. I wish I mean it will be 1/5 e to the 5x.
Exactly.
X plus c.
Exactly. This is going to become 1/5.
It's really a use of if you really wanted to show the work, but if you're watching this video, you probably know how to do this already.
Yeah, by now, yeah, if you know about integrals, this is chapter 6, so you guys should know about.
Why do you have the chapters memorized, Nick?
I don't know, I have no life. But I mean, the way I think about it is when you take the derivative of e to the 5x, you use the chain rule and you get a 5 in the front. So you're multiplying by 5. But since we're integrating now, we're basically dividing by 5. And the integral of e to the x is just itself. And then we have, of course, plus c. All right. And that's it for today. So that's all I got.
Remember to, what was the phrase? Like, I have the attention span of what? If you made it this far?
If you made it this far, then congratulations. You have a memory span, an attention span greater than a goldfish. Make sure to write that down in the comments below.
I have an attention span greater than a goldfish.
Make sure to smash that like button and hit that subscribe button as well. And turn on those post notifications, baby, so you never miss an upload from Nick's Algebraics.
I bet you no one's going to leave that comment.
Yeah.
Yeah, make sure to subscribe for more bangers, though. Yeah, more banger videos.
Absolutely. So thank you guys very much, and I'll see you in the next video.
Goodbye.
Have a good one. It's your boy, Peanut Butter Brother, signing out.
And I'm a random guy.
He's a random guy whose name is...